In unit number 3, we're going to be studying polynomial functions. In section 3.1, we're going to talk about characteristics of polynomial functions. When you look at the definition of a polynomial, it can be quite intimidating. However, if we break down exactly what it means, you'll find that it's not all that difficult. Okay? A polynomial is a function of this form where the coefficients, which are your a subscript n minus 1, so basically the numbers in front of your variable are your coefficients, and they can be any real numbers, okay? And the exponents on your variables, in this case the variable is x, have to be whole numbers, so 0, 1, 2, 3, 4, 5, etc. Okay, so that's a polynomial. The degree of the polynomial is determined by the largest exponent on an individual term. So for example, in this polynomial, the highest exponent is 4, it's degree 4. If we were to expand this and FOIL it out, your highest power on a variable would be x squared, so it's degree 2. All right, looking at this one here, what do you think the degree of this polynomial would be? Well, again, you wouldn't want to multiply this all out, but if you were to think quickly, if you multiplied x squared by x cubed, you get x to the 5th, and you multiply it by another x, you're going to add the exponent to get x to the 6th. So this would be a degree 6. All right, the degree also determines the maximum number of x-intercepts. So if there's a degree of 0, that means there's no x-intercept. A degree of 1, there's a maximum of 1 x-intercept. 2, there's a maximum of 2 x-intercepts, etc., etc. Now, just because something has a degree 2, for example, does not necessarily mean we are going to have 2 x-intercepts, and the easiest one you can think of would be a parabola that has the vertex at the origin. That's actually a degree 2, but it only has 1 x-intercept. All right, looking at quadrants, just to recall, quadrant 1, 2, 3, and 4, that should be a review. Now, when we talk about odd degree polynomials, we're talking about ones where the highest exponent is odd, so 1, 3, 5, 7. And those polynomials, their end behavior will be very similar to a line. So a positive line starts down in quadrant 3 and ends somewhere in quadrant 1, while a degree 3 and a degree 5 that has a positive leading coefficient will also start down here and end here. It just might have some bumps and squiggles along the way. Similarly, an odd degree polynomial that has a negative leading coefficient is going to start in quadrant 2 and end in quadrant 4. Similarly, it might have some bumps and squiggles if it was degree 3 or 5. An even degree polynomial is one that ends in has the highest power of 2, 4, 6, etc. And they're going to behave and have the same end behavior as a parabola, which is a degree 2. So a positive leading coefficient in an even degree is going to open up. It's going to start in 2 and end in 1. A negative will start in 3 and it will end in 4. Now, obviously, there might be more bumps and squiggles along the way. Whoops, I went the wrong way with that one. There might be more bumps and squiggles along the way. So, for example, you might have something that goes like this or something that goes like that. Okay, so but the end behavior where it starts and ends is going to be very similar to a parabola. All right, in this next set of 5 problems, we want to state whether each function is a polynomial, and if so, state the degree, the leading coefficient, and we've also added the constant, and we'll explain what the constant is. So equation A is a polynomial, yes. The degree would be degree 2, because the highest exponent is 2. The leading coefficient would be the number in front of the variable with the highest exponent, so it too would be 2. And the constant is the term that doesn't have a variable attached to it, and the constant in this case would be plus 2. All right, question B is not a polynomial, as it is not, that is an exponential equation because the variable is in the exponent. For question G, I would have to FOIL this out. So if I FOIL it out, I get 3x squared minus 18x plus 2x minus 12. And if you collect like terms, you'd get 3x squared minus 16x minus 12. So the degree, and this is a polynomial, is again degree 2. The leading coefficient would be 3, and the constant in this case would be negative 12. So that one is a polynomial. These ones are not polynomials. We've had 2 polynomials and 3 that weren't. If we look at this set here, again, we can quickly see this is not a polynomial because it has an exponent of x to the 1/2. Root x means x to the 1/2. This one is a polynomial, and it's degree 4. The leading coefficient would be 3, and the constant in this case would be 0. Absolute is not. This guy here is a degree 3. The leading coefficient, 2, and the constant would be negative 1. All right, now a couple of other things about graphs of polynomials. A degree 0 means it's just a constant. It would be a horizontal line. And these are on page 109 of your textbook, so you don't need to copy these down at all. Linear function is a line, obviously. Quadratic looks like that. A cubic looks something like that. Quartic. Quintic is a degree 5. So for the following questions now, we want to determine whether the degree of the function is even or odd, whether the leading coefficient is positive or negative, and state the number of x-intercepts and state the domain and the range. Okay, so first of all, this is an odd degree polynomial. So we know it's an odd because it starts in quadrant 2 and it ends in quadrant 4. We know the leading coefficient is negative because it looks like it follows a path of a line going downhill. All right, the number of x-intercepts in this particular case, there are 2 x-intercepts. And the domain and range, well, the domain is x is an element of the reals, and the range would also be y is an element of the reals. Okay, question B. Again, this is an even degree polynomial, and the leading coefficient is positive because it's starting in 2 and ending in 1. Okay, the number of x-intercepts, we have 2 x-intercepts, and the domain is all the reals, and the range in this particular case is y is greater than or equal to negative 5. For a polynomial, the domain will always be all the reals. The range, depending on what the degree is even or odd, will change. Okay, this one here is an odd degree polynomial. The leading coefficient is positive as it's starting in 3 and ending in 1. The number of x-intercepts, it looks like there's 2 there. So there's 1, 2, 3, 4, 5 x-intercepts. Okay. And the domain and range, again, the domain, x is an element of the reals, and the range is y is an element of the reals. Now, I'm sure you're seeing a pattern, but if the degree is odd, the domain and range are always going to be all the reals. All right. In this polynomial, we want to identify the type of polynomial. Okay, identify the degree, the end behavior, the maximum number of x-intercepts, whether it has a max or a min, and identify the y-intercept. Okay, all right, so first of all, this is a quartic. So for part A, it's a quartic or a degree 4. The leading, so the degree is 4. The end behavior, well, because the leading coefficient is negative, this thing is going to start in quadrant 3 and end in quadrant 4. The maximum number of x-intercepts is going to be 4. Whether the polynomial has a max or a min, well, because it is opening down, this guy is going to have a maximum. And the y-intercept is, if I let x equal 0, is going to be the constant. So the y-intercept is negative 4, or as a coordinate, it would be 0 and negative 4. Okay, question B. Okay, again, following the order of the questions, this is a cubic. Okay, the degree is degree 3. Identify the end behavior. Well, it's a positive leading coefficient, so it starts in 3, it ends in 1. Identify maximum number of x-intercepts. What's going to be 3. Identify whether it has a max or a min. It has neither because it's a odd degree, so there's no highest or lowest point. And F says, and identify the y-intercept. Well, the y-intercept this time is positive 3, or again as a coordinate 0, 3. Okay, I'm going to leave you to try these other ones here on your own. Okay, so C and D are going to be part of your assignment. Okay, now we want to match these 4 equations to their graphs. Okay, and we can tell by looking at the degree and the leading coefficient for the most part. Okay, so if we take a look at graph A, this one starts in quadrant 3, it ends in quadrant 1. So it's an odd degree polynomial, and the leading coefficient is positive because the graph is going uphill. So this one has to match up to equation B. For graph B, it starts in quadrant 2, it ends in quadrant 1, so it's an even degree polynomial with a leading coefficient being positive, so that one matches up to equation B. For C, I have a starting in 2, ending in 4. So this is an odd degree and it's going downhill, so it's negative. So this one is going to end up being graph C. And the last one looks like a negative even degree, and the only one that's possible is graph A. Okay, in our last example here, we're looking at a manufacturer determines that the profit of manufacturing skateboards can be modeled by the following equation, where X represents the number in hundreds of skateboards sold. What is the degree? Well, the degree of this equation is 4. The leading coefficient is 1.25, and the constant is negative 3,200. Describe the end behavior. Well, this is an even degree polynomial with a positive leading coefficient, so it starts in quadrant 2 and it ends in quadrant 1. What are the restrictions on the domain? Well, the restrictions on the domain are X has to be greater than or equal to 0 because you can't manufacture negative number of skateboards. What do the x-intercepts mean? Well, the x-intercepts basically mean that the profit's going to be 0, so the x-coordinates of the x-intercepts would represent the number of hundreds of skateboards to break even. So your break-even points are your x-intercepts. And the last question says, what's the profit from 100 or 1,200 skateboards? Well, that means I'm putting 12 in because in this equation, X represents the number of skateboards in hundreds. So it's going to be 1,000 times 12 plus 1.25 times 12 to the 4th minus 3,200. So if we work this out, 1,000 times 12 is going to be 12,000 plus so this is going to be 12,000 plus, let's take 12 to the 4th power, times that by 1.25. That's going to be 25,920, and I still have to subtract 3,200. So now if I add these all together, I'll just write the final answer up here. The profit will be $34,720. All right, so that is the end of section 3.1, characteristics of polynomials. So there's a short assignment for you. Plus there were a couple questions back in the slideshow that I said I could leave you guys to do. So you guys could try those as well. And if you have any questions, you can ask me in class.